Allora, molto brevemente, il professor Álvaro Cunha, che invito qua sul palco, è professore all'Università di Porto, è un'autorità nel campo del monitoraggio, in particolare il monitoraggio dinamico, ma non solo, delle strutture. Per chi fa ricerca in questo ambito, diciamo, Álvaro è veramente un nome molto autorevole, quindi lo ringraziamo della sua presenza. Chiederei alla collega professoressa Uva di darci qualche elemento in più sulla sua biografia e poi lasciamo lo spazio al collega. Grazie.
Grazie. Come ha detto Filippo, Álvaro Cunha che è un professore ordinario all'Università di Porto, alla FEAP, è uno degli esperti più riconosciuti a livello internazionale nel campo del monitoraggio dinamico delle strutture, dell'analisi dinamica strutturale delle vibrazioni. È stato tra l'altro direttore del laboratorio Vibest, laboratorio di vibrazione e monitoraggio proprio dell'Università del Portogallo, della University of Porto. Oltre a in questo campo infatti ha potuto sviluppare tantissime ricerche nel campo dell'analisi strutturale dinamica della vibrazione delle strutture, test dinamici su grandi infrastrutture civili, non soltanto, strutture speciali, non soltanto ponti, ma anche dighe in calcestruzzo, turbine eoliche, comunque ponti di varia tipologia e anche di notevole impegno. Si è occupato anche, grazie a queste sue attività, della progettazione e implementazione di sistemi di controllo delle vibrazioni e naturalmente insomma, del SHM, dello Structural Health Monitoring di strutture civili e di infrastrutture speciali. Menziono anche la sua partecipazione a numerose associazioni scientifiche e gruppi di lavoro, ne menziono giusto una, la più recente, che è comunque la presidente della European Association of Structural Dynamics, e difatti questo insomma, è un po' il tema di cui adesso sentiremo la sua keynote lecture.
Thank you very much. Good afternoon to all of you. First of all, I'd like naturally to acknowledge the very kind invitation from our colleagues and good friends, Filippo Bertini and Walter Salvatore, to have the opportunity to come here and share with you some of the modest experience we have got along the years in our laboratory at the University of Porto. It is really a privilege to participate in this event and revisit this so nice city of Perugia. I've chose as title of my presentation Dynamic Testing and Continuous Dynamic Monitoring of Bridges and Special Structures, Is It Worth? In fact, apart from making a very brief introduction to some basics of modal identification of civil structures, my objectives are essentially twofold. On the one hand, to stress the interest of dynamic testing and modal identification in different phases of the life cycle of bridges, design, construction, commissioning, and service phases. And on the other hand, to emphasize the role that continuous dynamic monitoring of bridges can play in different perspectives, in terms of vibration serviceability, safety checking, in terms of monitoring of dynamic effects and fatigue assessment, in terms of aerodynamic studies based on measurements on the prototype, or even in terms of vibration-based SHM. I will begin with this very brief introduction. As it is well known, the first modal identification tests have been based on knowledge that came from our colleagues from mechanical engineering using forced vibration tests. There was some attempts initially to build and apply exciters specifically designed for large structures, for bridges or dams, like impulsive exciters or servo-hydraulic exciters. But we could soon understand that when dealing with large bridges, it is really difficult, expensive, and cumbersome to use and apply large exciters that was made in some bridges like Tatar Bridge, but we could soon understand that the advances at the technological level in terms of transducers, digitizers, became feasible to use ambient vibration testing, and many different methodologies have been developed in order to extract accurate estimates of modal parameters based in some cases on spectral densities, in other cases on correlation functions, in other cases directly on acceleration time series. And we have nowadays even commercial software that we can easily apply for that purpose. After saying so, I'd like now to essentially follow the several phases of the life cycle of bridges, giving some examples of the usefulness of dynamic testing. At the design phase, it is well known that, at least in wind engineering, it is very important when we're dealing with large bridges to perform tests in physical models, to clarify aspects related with buffeting, with vortex shedding, lock-in, with flutter instabilities, with cable vibrations, and so on. But also in the field of seismic engineering, testing physical models of bridges can be useful. An example is the work developed in the past by our colleague of our group, Elsa Quintano, based on the physical model of the Jindo cable-stayed bridge. She could clarify the role that the distributed mass of cables can play in terms of the severity of the seismic response. Passing to the construction phase, different examples can be presented. The first one is related with the bridge that you can see in the left-hand side, Infante Henrique Bridge, a new bridge in our city, in Porto, to install a new line of metro. The construction of this bridge required a very complex construction procedure. It was necessary to build some provisional piers that were afterwards removed, and it was necessary the installation of retaining cables and suspension cables of the arch. And we have been contracted to monitor the evolution of the axial forces in these cables by measuring ambient vibrations. And we naturally based that on the vibrating chord theory that was applicable to most of the cases. In some other cases, we have to develop some finite element modeling for calibration. And this was a work developed during 15 months with more than 600 control points that was very useful for the designer and for the construction company. And this was also the basis in terms of knowledge and tools to be able to perform afterwards a more ambitious work, the evaluation of the axial forces in the cables of the suspension roof of the London Olympic Stadium some years ago. Also, in terms of the construction phase, I can give another example related with bridges with lively behavior, where we need to introduce some vibration control devices as TMDs, tuned mass dampers. In this case, we had an arch bridge, a steel bridge, that was prone to excessive vibrations due to joggers in some circumstances and also to continuous flows of pedestrians. So it was necessary to install two TMDs to mitigate these vertical vibrations. And dynamic tests were very useful in terms of the construction of the TMDs, and afterwards in terms of the accurate identification of the dynamic properties of the bridge, the tuning, the correct tuning of the TMDs, and the evaluation of the structural damping, and also the observation of the response of the bridge to continuous flows of pedestrians, in particular during the inauguration day. But a more paradigmatic case is probably the Coimbra footbridge, where since the beginning we could understand that this bridge would be prone to excessive lateral vibrations like those that occurred in the famous Millennium Bridge in London. So using the formula that was developed for that purpose there, we could estimate that about 140 pedestrians could trigger the lateral lock-in problem, so with a nonlinear increase of vibrations, assuming a 1% of damping. So immediately after the construction of the bridge, we performed ambient vibration tests to accurately identify the natural frequencies and the mode shapes of this bridge. The mode shapes look rather strange because the bridge is asymmetric both in plan view and in cross-section, so we have not pure modes. But this work was essential to develop a new finite element model of the bridge, to calibrate that in order to have a good matching between model parameters identified and calculated, and this permitted the evaluation of the model masses that were the basis for the final design of the TMDs. We developed also free vibration tests, releasing masses of 2 to 3 tons from different points of the bridge in order to create free vibration responses that were used to estimate accurately modal damping ratios. And we could notice then that the damping identified was about 1/2 of that had been used at the design. So it was about 0.5%, which increased the level of problems in terms of dynamic response. So we performed crowd tests with a group of 150 students from our school that we put crossing the bridge with an increasing number of pedestrians, and we could clearly understand that with 70 people on the bridge, the lateral lock-in was triggered, and we could reach a maximum lateral acceleration of about 1.2 meters per square second, which represents 12 times the limit, or the limit suggested by the footbridge guidelines, both by CETRA and HIVOS. So this required the design of an important TMD put at midspan by limitations of space that was splitted in 6 different units that whose oscillation contributed to mitigate the lateral vibrations of the bridge. And with this, we tried to increase the damping more or less 10 times. This damper is formed by an additional mass of 50 tons connected to the bridge by springs and dashboards duly designed in order to have a good tuning and a good efficiency. Anyway, after installation of the 6 units, we could immediately see that they had not exactly the same behavior, which reduced the performance of the dampers. And so we decided to make a forced vibration test using a shaker of 1 ton of mass constructed at our mechanical engineering department. And you can see here 2 plots with FRFs relating the lateral force induced by this shaker with the response in the several masses of the different units of the TMDs and the bridge. And you can see that in one case we have a very sharp peak that represents the damping of about 0.5% when the damper is not yet activated, because to activate the damper we have to overcome some friction in the rods. After activation of these dampers, you can see that the FRFs are clearly modified, and this peak is transformed in a smooth hill, which means that there was an increase of damping from 0.5 to about 4%. And this was enough to control the situation. However, it is probably at the commissioning stage that ambient vibration testing is more popular. And a classical example is the Vasco da Gama cable-stayed bridge. we have used there for the first time a wireless solution based on different seismographs, 6 seismographs, duly programmed and synchronized. We have used 2 pairs of seismographs in 2 reference sections, and the other 2 were moved along the deck and towers. We have used 27 pairs of points, 3 channels per point, 6-minute records, so every 20 minutes you move the set of measurement. And using the classical peak-picking method, we could get very accurate results at that stage. After that, we immediately initiated a very interesting and fruitful collaboration both with KU Leuven, the team of Guido de Rook, and also with Aalborg, Rune Brinker, and we could develop our own routines of more sophisticated methods like SSI, or poly least squares complex frequency domain, Polymax, getting nice results like this. It is interesting to mention that one component of the test was the free vibration test, in which we released a mass of 60 tons from the deck, increasing significantly the levels of vibration of the deck and creating nice free vibration responses. The mass was put in a barge. When the tide was low, the cables were cut, and we could get these very interesting results that were processed. Well, after this, we have tested many bridges in Portugal and abroad, and a very famous example, due to a nice collaboration with CSTB in Nantes, was the ambient vibration testing of Mio Viaduct, this very nice multi-span cable-stayed bridge designed by Michel Virlogeux with the collaboration of Norman Foster. And as we are not required identification of torsional modes, we decided to use only measurements along the central axis of the bridge. And just in one day, we could, using 4 seismographs, still synchronized, measure the bridge along 28 measurement sections, using also 16-minute records, and get very nice results. Here in this plot, we represent the first 10 modes of vibration in the range 0 to 1 Hertz. The red dots are the identified components. And I can say that only after getting these results, the designer provided us the estimates from the numerical model, and we are very, very impressive and glad, because there is extremely good correlation between identified and calculated values. And the same happens for the first 10 lateral bending modes, except for the higher order modes, probably due to the difficulty of the designer to conveniently model the lateral interaction between piers and foundation. Well, a more demanding example was the retesting of the Hamburg suspension bridge during the service phase of this bridge. This stemmed from a collaboration with our colleague James Brownjohn. In this case, we have used 10 triaxial seismographs, 6 from our laboratory and 4 from them. And we could use 76 measurement sections along the 3 decks of the bridge, upstream and downstream. As the bridge is very, very flexible, we decided to increase the time of observation per setup to 1 hour with 2 pairs of references. So this required 5 days of testing. Testing in England, even in summertime with rain and long distances. So it was a more demanding test. The information collected was immediately processed in the field using the classical peak-picking method, and you can see in the left-hand side above average normalized power spectra And it is interesting to see that due to some peculiarities of the boundary conditions, we can observe that some mode shapes are global mode shapes of the bridge, others are local mode shapes of each one of the three spans of the bridge. That can be understood taking into account the coincidence of the peaks, because there we have the representation of those spectra for the three different spans. At bottom we can see some stabilization diagram, because we applied afterwards also the stochastic subspace identification technique, extracting accurate estimates, for instance, of the first 8 vertical bending modes, also in the range 0 to 1 Hertz, of the first 4 torsional modes, and finally of the first 6 lateral modes. So a large number of modes of vibration in this range 0 to 1 Hertz. And I call your attention that the fundamental mode has a period of 18 seconds. Even so, we could identify accurately this frequency and mode. I can say that, in fact, using a wireless solution with high sensitivity sensors, with a good spatial coverage, using times of observation enough long to get high frequency resolution, and using, of course, robust and modern identification algorithms, we could deal with large structures with very low natural frequencies, with low damping, with some significant modal interaction, and getting good results. However, since 2007, our focus has been on continuous dynamic monitoring, and we have tried to make different implementations in different structures with different topologies. In fact, we deal with many structures, many bridges that get older and older. Some are complex systems, and so it is useful to take into account the advances in measurement technology, in data processing and retrieving, and this naturally creates an increasing interest in terms of permanent dynamic monitoring, and we need, of course, to develop appropriate software and tools to extract relevant features from the collected data and make online evaluation of the bridge condition. I'd like to stress different perspectives of monitoring. I will begin with the simplest one. I recall the example of Coimbra footbridge, that bridge that could have lateral vibrations and that deserved the introduction of TMDs. The owner required also, for prudence, the monitoring of the bridge during 5 years. We have introduced a simple system with these 6 accelerometers. We have developed a LabVIEW application to provide immediately information to the designer, to the construction company, to the owner and ourselves. And after a couple of years, we could very well demonstrate that the TMDs had been efficient, because during all the period observed, the maximum daily lateral acceleration never exceeded 0.1 meters per square second, which is the value recommended by the guidelines. During those dynamic tests before the installation of TMDs, we had 12 times this. Another perspective is the use of continuous dynamic monitoring to characterize the dynamic effects of road traffic. An example was the study developed with the collaboration of a former student that is presently our dean at Porto, Rui Calçada. In this bridge, we have evaluated dynamic effects taking profit from the use of the heavy trucks used for the static test at the commissioning stage, and we could measure the dynamic effects induced by this traffic, also due to some poor conditions of pavement roughness that caused some interaction. And we could measure these effects both using embedded strain gauges in the concrete and also some load cells interposed in some strands of stay cables in collaboration with Freycinet. Also in railway bridges, we have tried to characterize dynamic effects. This is a bridge built after the Second World War. We have developed initially an ambient vibration test to calibrate an initial finite element model of the bridge, but subsequently we have also implemented a monitoring system based on electrical strain gauges, introduced in different important structural elements of the bridge, also in some rails outside the bridge, in order to be able to characterize the real traffic passing on the bridge. This permitted to make a characterization, an exhaustive characterization of the fatigue condition of the different structural elements, permitted to understand which were the critical elements in terms of fatigue, and afterwards we developed a more sophisticated approach that permitted us to understand better a local fatigue problem induced in some lateral or transversal beams over the abutments and the central piers. In this case, some higher order modes of vibration of these structural elements were excited by the traffic. And this study was developed in the context of the FATLESS project coordinated by Walter Salvatore some years ago. More recently, my colleague Elsa Keden, together with Zhen Sun, a postdoc of our group that is nowadays full professor in China, together with João Santos from our National Laboratory of Civil Engineering in Lisbon, the entity responsible by continuous monitoring of Lisbon Suspension Bridge, they were able to develop a different approach using wake in motion, vision, and artificial intelligence. It was possible to classify the railway traffic and predict fatigue damage caused by specific trains. Now, moving to a different direction, some years ago we have been contracted by a French company, CETEC, to manage the monitoring system of a very nice bridge built in Reunion Island in the Indic Ocean, island under French administration. In this bridge they have introduced 5 anemometers, 14 pressure cells, 6 thermometers, 6 accelerometers, this information coming from the prototype during a couple of years was really very important, permitting to develop comparisons in terms of the behavior of the bridge measured and predicted at the design stage. Another different aspect has to do with the influence of environmental and operational factors on the modal variability. When we moved to our new campus in 2000, we had there this very nice stress ribbon footbridge designed by a colleague of ours that worked with in Stuttgart with the team of Professor Schleich. And so this was a very nice research case for us. And my former PhD student, Waiwa Hu, that now is professor in Shenzhen, implemented there a monitoring system that permitted to understand clearly the very high level of importance of temperature on the variation of the modal frequencies. And after understanding this and how to deal with this, we decided to develop a strategy for vibration-based damage detection. And the strategy consisted in getting or collecting acceleration time series from different channels in a bridge, every 30 minutes we collect data and we immediately apply robust homemade software for output-only model identification. And making the tracking of the evolution of the natural frequencies, it seems that they are stable, but in fact they are not so stable. Making a zoom, we see that we have not only daily variations, but mainly seasonal variations, induced in this case especially by temperature and intensity of traffic. And so we need to apply suitable statistical methods to mitigate these effects in order to finally be able to build appropriate control charts where some suitable novelty index stemming from the variation of frequencies is able to flag the existence of some abnormal change, structural change. This was applied for the first time in the context of a PhD thesis from my colleague Felipe Magalhães on the Infante Henrique Bridge with 12 accelerometers disposed in 4 different cross sections and advanced techniques for output-only model identification were implemented in an automatic and robust way, taking profit from a hierarchical clustering algorithm that permitted to create the different clusters of estimates associated to the different types of mode shapes. In the left side, you can see here the tracking of these natural frequencies, the first 12 natural frequencies in the range 0 to 5 Hertz. During 1 year, it seems that they are stable. Making a zoom to one of them, you can see that, in fact, we have daily variations and seasonal variations. And on the right-hand side, you can see these variations for the first 4 natural frequencies during 3 years. And the influence of temperature is very, very clear. We can even see more clearly this correlation. In the left-hand side top, we have a correlation of 1 natural frequency during 1 year with temperature in inverse scale. And this correlation is very evident. At the bottom, we can see that also at the beginning of the morning in some days, there are some traffic jams, and the intensity of traffic creates some influence over some natural frequencies. So it was really important to develop a multiple regression model to mitigate these effects. And you can see in the right-hand side the estimates of 1 natural frequency during 2 years at the top without this mitigation. And after applying these techniques, the range of variation of the estimates was just about 5 millihertz. So after understanding this, we got confidence in applying vibration-based SHM. Of course, that the bridge was new, so it was necessary to create some numerical simulations, in this case, 4 different damage scenarios, where we locally introduced some small reductions of bending inertia, but creating relative variations of natural frequencies of just about not more than 0.2%. And then using 2 years of data, in terms of modal frequency estimates, we changed the estimates of the second year using these percentual variations stemming from the simulations in the numerical model. And what we have seen was that developing the design of the control charts, in all 4 cases we have been able to see that the control charts were able to flag the existence of some abnormal change. So we are not identifying the location of damage, but we are at least being able to detect that some abnormal change occurred. This was replicated in a service required by a company that was interested in the construction of a dam. You can see in the left side the dam that was built upstream 2 existing bridges in a tributary river of Douro River. a steel railway bridge and arch concrete bridge, there was some concern that the blasting operations associated to the construction of the dam could affect these two bridges. So we have been contracted to implement vibration-based SHM systems in these two bridges, and moreover, also to use geophones to control the levels of vibration induced by the blasting operations. Anyway, I use this example to say that vibration-based SHM is not the only solution. We must be aware that we must combine always information from this component of monitoring with others components. In this case, the piers of the railway bridge were very sensitive to variations of flows, also to works in the foundations to create a channel for pumping the water from the main river to the new reservoir. And so our National Laboratory of Civil Engineering imposed to complement this system with the introduction of a static monitoring system composed by clinometers that were introduced in these piers, and they established also some thresholds for variations of inclination in these piers. At last, I'd like to say that although our strategies to damage detection have been based essentially on the variation of modal frequencies, in our research unit, other colleagues developed alternatives. For instance, our colleague André Machado, in collaboration with Rui Calçada, have developed an interesting machine learning strategy for early damage identification based on train-induced dynamic responses. They use autoregressive models. They play with the parameters of these models, and they demonstrated the feasibility of detect damage just based on the measurement of these dynamic responses due to the passage of trains. So, just to finish this component, I'd like to show you the challenge that we are facing nowadays. This nice bridge is not existing yet, and they will be constructed in Porto during the next 2 years, I hope, and we have been contracted to process the data from the monitoring system of this bridge. Our work will have 3 components: vibration-based monitoring of axial forces during the construction phase, vibration-based SHM, based on model tracking, and machine learning damage identification based on train-induced dynamic responses. At last, I just would like to stress that this technology we developed for bridges can be easily extended to other types of structures, and we have been doing so in terms of wind turbines, first on onshore wind turbines, more recently also in offshore. For instance, here we can see that using a similar technique, we have been able to get the clusters of modal estimates that we represent here in a so-called Campbell diagram, relating the frequency estimates with the rotor speed. And beyond these horizontal clusters, we notice also some inclined clusters that have to do with frequencies of the rotor. Also, an interesting aspect has to do with the evaluation of aerodynamic damping that we can feel, for instance, in the first fore-aft tower mode, so in the direction perpendicular to the rotor plane. The damping increases significantly with the wind speed, and that doesn't happen naturally in the side-side mode or direction. In this case, we have also defined several damage scenarios, taking or based on real values measured and mentioned in the literature in terms of variations of natural frequencies associated to skew in offshore foundations, to foundation damage in onshore, or with blade damage. We took into account several environmental and operational factors like wind speed, temperature, rotor speed, blade pitch angle. And the application of the same techniques could also demonstrate the feasibility of detecting some abnormal structural change in most of the cases. And to finalize, I'd like to mention that even in the most challenging structures that are concrete terms, where the structural levels of signal are of the order of micro G, it has been able to get good results. In this case, we have been responsible for the monitoring of this dam using 12 accelerometers spread in 3 different galleries of the dam. And we monitored the bridge even since the beginning, so during the first filling of the reservoir, which is a very interesting phase. And there was, in this case, a very sudden increase of water level, and immediately we can see a very significant decrease of natural frequencies. So we could analyze the correlation between the variation of water level with natural frequency estimates, and beyond that we could also analyze the influence of temperature, which is not so significant but exists. And the same type of conclusion was obtained. With the support of our colleagues from the Department of Dams of LENEC, it was possible to create different realistic scenarios of damage, to idealize that in suitable finite element models, to introduce small damages, evaluate the levels of variation of natural frequencies, and introducing these percentual variations in some part of the time of data collected, we could create control charts that also permitted to conclude the feasibility of detecting damage in these cases. So I can conclude saying that we have presently technology available, both in terms of accelerometers and digitizers, but also in terms data analysis and control and transmission systems that permit us to develop very accurate and reliable model identification tests and develop continuous dynamic monitoring programs, and the high quality databases created can be used for different perspectives, as I could mention in this presentation, related with vibration safety checking, with evaluation of traffic induced effects and fatigue assessment, with aerodynamic studies, with measurements on the prototype, influence of environmental operational factors on the model variability, or vibration-based SHM. So this is the contribute I can give. I just regret not to be able to speak in Italian, but I hope you could understand. So thank you.
Thank you, Alvaro. Really great keynote presentation. So your work was instrumental to developing an approach that you have seen and you will see also tomorrow that ANAS is applying in 1,000 bridges in Italy right now with the help of Fabre Consortium and some other universities. So your question was, is it worth? So we can say it's worth, right?
Yes. This is not a miracle, but it gives good results. It has given good results. And I must say that at the beginning I was a little bit suspicious because, in fact, we deal with very small variations. And we have to take into account the disturbance caused by temperature, intensity of traffic, things like that. So, but the results demonstrate the feasibility of using this technique in these cases. But I always like to say that this is a component of monitoring. There are other components, and if we can combine them, we can naturally get much better results.
Yeah,
okay.
Thank you. We are all on the same line. Thank you.
Okay,
thank you, Álvaro.